All right, thank you very much for the invitation to be here on this quantum simulation conference and tell you a little bit about our results. And I think it connects very well to what Toby has been talking about before, because we're going to talk a lot about the Fermi-Hubbard model as well in this talk as a reference model to see what we can do in analog quantum simulation in regard to that. So I'd like to tell you about a few things, mostly focusing on the fermion work, because I think that's maybe most interesting to you. But I hope I'll also get to some new results on non-equilibrium dynamics in 2D Hilbert space fragmentation and observation of fractons, and just polar molecules, just maybe as an outlook, as a new platform in the end that we're very interested in. So actually, I started 20 years ago working in quantum simulations. And it's interesting to see how the community here actually perceives quantum simulations. I think it's a bit broader, it's become a little bit broader what we thought about initially when we started these experiments. So I think for me, still the most, approach close to quantum simulation is what we call analog quantum simulation, where we try to implement a certain Hamiltonian in a physical system directly, and then we can look for the ground states or dynamical evolutions of the system. And this is, of course, an extremely powerful approach. You'll see that for fermions here. You'll see that for XY models, Ising models, transverse Ising field models, things like that. And however, of course, it's not universal. You can only do what you can implement actually on the machine. And then you have the other approach, what you also call quantum simulation. I would call more quantum computing, but maybe we can settle and call it digital quantum simulation, where you have gate-based circuits, non-error corrected, yet of course, if it will be error corrected, it will be a full quantum computer. This is very nice because in principle it's universal. You can build up a lot of dynamics or Hamiltonians from this. But as we've seen, very often it can be resource hungry. I just remind you of the talk we heard on laser fusion, where we had gate counts of 10 to the 20. That makes it a bit challenging to do in the experiments. So I would like to stress on the first point here, because also this is funded by the Institute for Robust Quantum Simulation, so I'm interested in that. I would like to point you to this interesting paper from my colleague Ignacio Siraca and Raul Trivedi at MPQ, where they actually looked at the first case of implementing analog quantum simulation, and they found actually the nice thing that we have in analog quantum simulation, that even if we have a constant error rate throughout the quantum simulation, even if we are not perfect in these situations, we still have a notion of robustness in this type of approach. And this, to me, intuitively connects, because what you're basically building is synthetic matter, and phases of matter in nature are not fine-tuned to specific details. So they have some certain robustness built into that. And to capture that in a mathematical language, to prove that, I think that's of course a challenge, and this is what Rahul and Ignacio just did, and this is the new paper in 2024, which I point you towards this. So you can get very, very useful things out of that, even if you have extensive amount of errors, because in the end of the day, you're mostly interested in intensive quantities in condensed matter physics applications, for example, which are still robust to these extensive amount of errors. So again, this started for me, in 2000, this work, entering this field of quantum simulation based on this idea of Ignacio and Peter, that we could look at the physics of strongly correlated quantum systems, strongly correlated condensed matter systems. And by now, we've seen in this conference also, there's just this plethora of platforms. I think it has actually become the major application of quantum computing. Quantum simulation now is the major application field, as we've actually beautifully seen in this conference also, with this vast set of diverse application areas. So just to introduce you our system, the optical lattice platform, this is kind of creating optical potentials through interference of laser beams. And here you can see an optical potential created by kind of 5 laser beams, giving rise to this kind of quasi-periodic potential, and we can load ultra-cold atoms into these optical crystals, which define our materials, and we can have different spin states, which would encode, different kind of spin states of an electron in that system. So I think the very big advantage of doing that with ultra-cold atoms, and I think I only know the quantum dot platform which has similar capabilities, that we can do this with fermions directly. So we can directly put fermionic atoms into the system. We don't have any overhead in the mapping of the electron problem to spin problem. So we can directly use fermions. We directly have exchange statistics built into the problem, which is of course a big advantage. So in recent years, we've learned how to actually make these things also more programmable. For example, how with a push of a button, we can realize different lattice configurations, square lattice, hexagonal lattices, triangular lattices, Kagome lattices, leap lattices, all basically without having to rearrange all our laser beams in a complex setup, but really at a push of a button, we can change between those configurations, which of course typically would require you to synthesize a new material in a very complex way. So that's very nice, and we'll maybe see a few of these results as we go on. The next big invention in the field was really the invention of quantum gas microscopy, that we're able to detect individual atoms in these lattices. Here's a picture of one of my former postdocs, Jae-Yoon Choi in Korea, showing this beautiful picture where you see each of those individual atoms lighting up on this square lattice with a very, very good signal-to-noise ratio. And this picture shows two things. We can see the individual atoms. We can do this also for large-scale systems. So these are few thousands of particles that you can actually look at and do these simulations for these fermionic particles in lattices. We can shape the external potentials basically almost at will to a large degree using digital mirror devices, projecting arbitrary potentials onto them, create ladder systems, 2D systems, 1D systems, different geometries, different terminations on the edges. All of that is possible really by just the power of projecting optical potentials onto these atoms that we trap in our vacuum chambers. So one thing for electrons that's of course important is that you basically, when you want to look at strongly correlated electrons, you need to distinguish a few states. So not only you need to distinguish whether there is an atom or no atom, you actually also want to know whether it's a spin up or a spin down particle corresponding to the spin state of an electron in a material. So how we do that in the experiment is the following. Imagine you have the physical system, which is this monolayer here, this two-dimensional system. Well, that's the system you analyze, the Fermi-Hubbard model. Then we actually apply, just for detection, a Stern-Gerlach separation, which pulls the spin-ups into an upper layer and the spin-downs into a lower layer. Then we'd use a Thouless charge pump to separate those two layers, and then we can just take two photos of these separate layers, one corresponding to the spin-ups and one corresponding to the spin-downs. Then we just have to add them up together, and then you find the original occupation of your system that you had, right? So you know where the spin-ups, spin-downs are, the double-ons, the hole-ons, all the four states that you can have on a lattice site can be distinguished in this way. And if you do a measurement process on a strongly correlated system, this basically, corresponds just in a collapse of the wave function to one of those configurations, which you see by random in one of the experiments. And then you have to repeat the experiment thousands of times to, at the end of the day, get probability distributions of those different configurations. And from the probability distributions of the configurations, we can then calculate physical correlation functions. And I'll show you examples of those and why these are very interesting. What's important, of course, if you have access to these snapshots to probability distribution of configurations, you can calculate non-local correlation functions beyond simple two-point correlation functions, what you have in condensed matter physics. So now also things like hidden order parameters become accessible actually in experiments. So another point I want to dwell a little bit on is some new work on actually not only having where we're able to measure the occupations on the lattices, but we're also able to measure basically currents or kinetic energies. And this kind of introduces this idea of an orbital qubit, a spatial qubit. Usually you think of the qubit encoded in two spin states, spin up and down. Now I'd like to make you think about a different type of qubit, encoded actually in the orbital degrees of freedom, and I'll show you why that's important. Actually, I just learned that Ruichui Mao and his group in superconducting qubits had also very nice related work on this using superconducting systems. So the idea is the following. Imagine you have a 2D system that I showed to you before, and you're able to project this system now just for detection or manipulation into an array of disconnected double wells. And now the particle in this double wells is going to be my qubit that I can manipulate. So if you think of each of those double wells as corresponding to two modes, left and right, this would be like my spin up and spin down. Then we have kind of an orbital kind of Bloch sphere where we can think of the z direction of the Bloch sphere corresponding to the density occupation, density difference on those two sides, the x direction corresponding to the kinetic energy operator, and the y direction corresponding to the current operator. And all of these, of course, can just be accessed by doing corresponding rotations on this Bloch sphere, x rotations or z rotations to access all of those states. How do we do x and z rotations? Well, in this double well, an x rotation is just tunneling between the two lattice sides. A z rotation would be just detuning this double well and acquiring a phase shift between the left and right side corresponding to a z rotation. So that's exactly what you have in mind for the spin states now mapped onto real space. So just to give you an example how this pans out, how you can actually, through measuring the density difference in the right and left well after a certain time evolution, how that corresponds to the current operator. If I calculate the time evolution of this density difference, you see at time 0, no tunneling, it's just the original density difference. But if I wait for a quarter of a Josephson oscillation period here, then this cosine term will become 0 and this sine term will become 1. And then you see what you've actually measured in the density difference is just the current operator. So this would just correspond to a rotation around your x-axis by 90 degrees. If you combine that with the pi/2 pulse along the z direction by just detuning your double well, then you can actually see you can then measure the kinetic energy on those bond of sites on this double well systems in a similar way. So all of these become accessible, current, kinetic energy, and density differences, and that's nice. The kinetic energies, of course, if you're thinking about VQE, this is a way how you directly measure kinetic energy on those sites. If you actually want to prepare different things also on this double well, you have now ways to do that. Let me just show you how this works. So this would be just a standard kind of tunneling operation between the sites. This would be a Z operation. We can also do something like photon echo, spin echo on this orbital Bloch sphere. We can measure different current correlations in the system. So now we choose our measurement basis to measure the current operator, and we imprinted in the experiment a certain current pattern on this 1,000 qubit system. Then for theory, we expect this current correlations in the system, and this we can now measure through this approach in this orbital Bloch sphere. We can measure those current correlations and show actually very good agreement with the experiment. We can not only do that globally in parallel on all double wells, but we can also introduce local operations. We can locally manipulate this qubit by basically introducing local Z rotations, just a local potential energy offset, which introduces a local Z rotation, which now allows you to, say, measure the current operator on one bond, on the next bond, measure the kinetic energy operator. So now you can also choose at which kind of bond you want to measure which kind of operator in the system. And finally, this also is nice because you can prepare now very interesting orbital quantum states in your system by introducing these local operations. You can not only use them for readout, but you can also use them to prepare more complex kind of quantum states, initial states, which might be interesting for quantum dynamics, where you set up your system to have a certain current pattern, kinetic energy pattern, and then you look at the quantum evolution of that. All right, I'll come back to that orbital Bloch sphere in a little bit when we talk more about the Fermi-Hubbard model, but I want to go on and show you now results, what state-of-the-art, quantum simulators can achieve on the Fermi-Hubbard model, and I think that's very nice to compare to the digital machines now, because this is the reference problem, as Toby has said, and I would be really happy to see how the digital machines are performing on similar problems. So what we try to understand is, of course, this complex phase diagram of the Hubbard model, where we know if we are at half filling, in the undoped case for strong repulsive interactions, we have antiferromagnetic ordering. And then when we dope the system, we have these kind of interesting phases, which we're really trying to understand what type of order is present here. And as we lower temperature, we of course expect this D-wave superconducting dome for certain conditions in the system. Now, if you try to break down this question, what are you actually trying to find out about physically? It's actually the competition of magnetic ordering. Without doping, we know the Fermi-Hubbard model maps onto the antiferromagnetic Heisenberg model. That's easy to solve. We know how to deal with that. But as soon as we put dopants into the system, it gets really hard. And so what we're trying to understand from a physics point of view is, how do these holes that move around in this antiferromagnetic order, how do they compete with each other? And let me already show you that at the level of single dopants, this is kind of interesting. But to show you how we measure this, how we actually tune our physical analog quantum simulator up to do these measurements, I want to show you how this is done in our experiments. So we have a square lattice. On top of a square lattice, we can project these kind of confining potentials. So we have a flat region here, which is the physics region where we do the experiments, the homogeneous system. And then we have reservoir regions at slightly higher energy where also atoms are floating around connected to that. So you could think of that as the leads of your material. Now, in a material, if you want to tune, for example, into a Mott phase, what you would do, you would apply a certain voltage to the material to tune the chemical potential. So we can do exactly the same thing. We can just lower the depth of this central flat region relative to the reservoir, and this sets the chemical potential in our system and sets the level of dopants in our system. And we can tune, for example, into a regime where you see here this beautiful n=1 plateau, the Mott plateau at half filling, surrounded by the reservoir, which is a metallic reservoir. And if we look at particle number fluctuations, for example, what I find always striking, you see this transition from Mott to metal happens within one lattice site, and we can resolve that difference, how this variance, particle number variance, shoots up within one lattice site going from Mott to metal. So we can now, on top of that, add the spin resolution capabilities and do the spin resolve detection. Then I can not only see that there's one atom per site, but I can also see where the spins are, and I can measure the spin-spin correlation function in my system. And you can see we also are in a regime where we have nice antiferromagnetic spin correlations in the system. So for the undoped system, we are at the antiferromagnetic Heisenberg point, and we can compare to quantum Monte Carlo simulations, which for the undoped case are simple. They can be done. And you can see actually we have very good agreement over the entire system size, and from the fits to QMC we can find out at what temperature ranges we are carrying out the experiments actually. So that's a good reference point just for us to know where we are. So now let's dope the system, and now is where all the problems start, where quantum Monte Carlo will start to fail at some point. And so that's, of course, the interesting regime we would like to look at. So what can we expect from physics, to happen here? If we have the antiferromagnetic Heisenberg model, just a cartoon picture here sketched as a Néel state, and we have holes moving around. If you're a hole, to minimize energy, what you really want to do is you want to delocalize, right? You want to delocalize and spread out in space. However, if your hole starts to move, you see then the green spin has to move in here, the hole moves by one side, the hole moves another side, now the red spin moves in here. What you're actually doing, you're damaging the antiferromagnetic background. And the more you're moving, the more you're damaging the antiferromagnetic background. So you're paying more and more energy, the more you're separating from your original site. And that actually leads to a very beautiful picture that Eugene and Fabian kind of pointed out in recent work. If you calculate the energy cost of the hole separating from its initial position, you find actually that there's a linearly increasing energy cost for this particle to separate. And now if you think about linear energy costs with separation, this is like quark confinement in mesons that we have. In nuclear physics, we have the same phenomena, and we know what happens. We get new particles that emerge, that are, of course, the hadrons, the mesons, the baryons that emerge because of the quark confinement. And of course now similar physics happens here. We also expect new particles to emerge, and the new particle that emerges here in the context of the Fermi-Hubbard model is what we call a magnetic polaron. It's the impurity surrounded by a dressing cloud of modified spin correlations, and whenever this impurity moves around in the lattice, it has to drag around with itself this huge kind of spin correlation cloud, distorted cloud, as it moves in the lattice. So now actually using quantum gas microscopy, we're able to directly measure the structure of this polaron for the first time, real space pictures. This would be, of course, a good test to compare to a digital machine. Can a digital machine calculate a correlation function like this? This is already almost impossible for a classical computer to calculate these days. Okay, just to give you a reference. So this is data coming from the quantum simulator showing you a 3-point correlation function. So let me walk you slowly through this. So we have dopants in the system, holes or doublons, right? Let's say we find a hole at one position in space, and now we're asking ourselves, how are the spins in the vicinity of this hole actually distorted relative to the background spin correlations in my system. This is what the C stands for. We're evaluating a connected correlation function. So we're always subtracting the standard antiferromagnetic background. That's trivial. We don't want to know about that. We want to know how is the spin background distorted because of the presence of the impurity. So I'm correlating the position of a hole here at position R with how the spins at position R plus I and R plus J are modified. And this is now shown in this 2D graph. So this is the position of the impurity in the center, and then you have lattice sites here, those two lattice sites, and I'm showing you the spin correlations between those two sites as this red bond that you can see here, and the color indicates the strength of the spin correlation relative to the antiferromagnetic background. And you can see that this is actually a huge dressing cloud that you see here that this impurity drags around with itself. And here's some first QMC from kind of Lode and his colleagues, and you can see that they still have already limited in getting out to the distances we're evaluating here in the experiment. Just to show you a little bit more quantitative, how we can plot this in a more quantitative way, showing you this Polaron structure distribution, we can take out all this antiferromagnetic staggering and plot basically the distribution function, something like a charge distribution function for a meson, like the structure distribution function of the spin surrounding the impurity. And you see it actually has a very interesting two-shaped component. It has a dense core and a very long-range kind of halo surrounding this kind of denser core. And for me, this is the first time anybody has measured this, and we're trying to understand this, where this is coming from, and what the meaning of this is. But now, of course, the next thing is to show what happens if you, for example, dope the system more and more. So the picture for individual impurities is the one where you get the polarons, but you actually already see that when we change the doping level by just tuning the chemical potential in our system, we get kind of very, very different structure distributions in the system. And in fact, we expect actually a crossover from a case where the polarons are the charge carriers to a situation when the doping is very large, where you're back to Fermi-liquid situations, and then somehow you're crossing in between in this kind of pseudo-gap region, and we're trying to understand when does this crossover between polaronic correlations and the Fermi-liquid happens, and how is it connected to the pseudo-gap. So we can take our data and now plot the doping here, and we see actually that around a kind of 15 to 18% doping level, we see this crossover from the kind of polaron to the Fermi-liquid happening in the system. I'd like you to remember this 15 to 18% doping level, because it's very close to where macroscopic kind of quantities, thermodynamic quantities, also show, for example, entrance into the pseudo-gap phase that you can see here. All right, let me move one step further and explain another kind of thing that we came up with. When thinking about these experiments, we obviously thought, well, how can we achieve high TC? How can we achieve better, higher temperature, jump temperatures, superconducting temperatures? How can we have higher temperature binding mechanisms that we can already see at the temperatures we're working at in the system? And in order to understand, first of all, where the binding actually comes from in the Hubbard model, it's actually good to understand that the binding of hole pairs that lead to Cooper pairs and superconductivity actually arises purely due to magnetic correlations in the system. So let me show you this toy model to make you understand why holes are bound together in this antiferromagnetic background. So imagine you have a ladder system, just as a toy model for us now, where you have strong antiferromagnetic couplings along the rungs. So you have these rung singlets here, and we put two holes into the system. So now if this first hole starts to move here in this direction, it will actually destroy the antiferromagnetic couplings that you can have here. So that's not good, because that will cost you a lot of energy. But if the second hole actually follows in pursuit and arrives at the same position as the first hole, then you've undone the damage of magnetic correlations, and you've actually recovered the original energy in the system. So here you've actually have a situation why when the second hole follows to the same position, you actually undo the damage, and you find a binding actually of these hole pairs. So what we actually are missing in this picture, and why in true ladder systems the binding is still extremely low, is that the kinetic energy cost of having two holes close together is still rather high, because remember, holes want to delocalize, and if you already have one hole next to another hole, it cannot delocalize anymore. So from a kinetic energy point of view, this argument actually doesn't hold very well, and actually shows that these hole pairs are actually disfavored if you take that into account, or lead to an extremely weak binding and therefore very low temperature for superconductivity in the system. So we thought about what can you do about that to actually engineer a material that does not have this penalty. And one way of doing that, to understand that, is actually that you can go to a so-called mixed dimensional situation where you actually allow the holes to only move in one dimension, but the spins can actually talk to each other in a two-dimensional setting. This is actually very easily done by just tilting those ladder systems, introducing an energy offset between the A and B sides of the ladder, so a hole cannot move from A to B because the detuning is larger than the resonant coupling, but the spins are a second-order hopping process. They are still allowed, and they can talk to each other, so super exchange is still there in the system. So if you do that, you actually find you remove this kinetic energy penalty, and now the binding energy shoots up by almost a factor of 15 to almost the full exchange coupling that you can see here. And now you indeed find, if you measure the hole-hole correlations in the system, you indeed find that you find a positive hole-hole correlation signal, a hole pairing signal compared to the kind of anti-correlations of the holes if you would have a standard ladder configuration. So really easy trick to actually boost the binding energy by almost an order of magnitude. So you can ask, of course, whether this extends also to two-dimensional systems, whether we can see some things like stripe formation or extended density structures, which will be the next level of correlations you expect in these systems. So we did the experiment again now in a 2D setting, and indeed we find actually indications for first signatures of stripe formation in the system. So here I'm plotting the hole-hole correlation map in X and Y direction for our two-dimensional system now, and you see that holes actually are anti-correlated when they're within one row of the system. That's just Pauli repulsion of the holes. But when we actually go along the vertical direction, you see the holes actually want to align with each other and show a positive hole correlation signal. And you can actually even see a next stripe forming up here at a certain distance. There's again a positive hole-hole correlation signal showing up. So we also have evidence for a kind of stripe formation in these systems, for holes to cluster up along these lines of stripes that we have in those systems. So let me skip that here. Let me just mention that this also extends to this general idea, not only present in ladders or 2D systems, but actually also would extend directly to bilayer systems, where you would apply an energy offset between those two layers, restricting the mobility of the holes to one layer, but spins talk to each other between layers. And that again leads to very tight binding of the holes across the layers with very large kinetic energies, and should lead to a very high jump temperature for superconductivity. And so this sounded very artificial to us in the beginning, can you have such materials? But then last year there was actually this very spectacular discovery of a new superconducting, high TC superconducting compound. So it's not LK99 or lithium hydrate I'm talking about, another one, where you actually in the nickelates found a superconductivity above liquid nitrogen temperatures in these systems. And then people started to analyze the band structure of these systems, and they found that they actually precisely model this kind of mixed dimensional setting where you have kind of mobility of the holes only in one plane of the system and spins talking to each other between the planes as well as within the planes of the system. So actually that's very nice because it's first time I think where we find a new mechanism for superconductivity, for new pairing energy, new mechanism for superconductivity through quantum simulation that is validated afterwards also in the experiments you find in real materials. So where are we right now? Let me just put this in perspective. We are kind of from a temperature regime starting to enter this interesting regime of pseudogap, where I think most of the ununderstood physics is happening, where we don't really understand what the order parameter is in this system, how we get from the polarons to these extended kind of charge structures that we're seeing, for example, stripe formation at lower temperatures and what happens in between. And I think what's really exciting, what quantum simulation really offers now, is that we can connect macroscopic thermodynamic quantities, which we can measure, like conductivity, compressibility, magnetization. We can now add a microscopic picture of what is happening in the system at a microscopic scale to that. And that offers, of course, new ways of testing your effective models. And, theorists like Subir and others, they are actually starting to take the experimental data from the quantum simulator and test their effective theories against that. So I think that's a real value that you offer. And of course, it would be fantastic if we could have digital quantum computers also calculate the same quantities so we know where are we actually there. I think they're far away from doing something like that, but well, we should discuss this. I think maybe it's a good point for the discussion session to get into an interesting discussion on those points. All right, how am I doing in time actually? Okay, so let me maybe before I close the fermion part talk just about mention just very interesting other work from colleagues in the field. So there's very nice work from Martin Svirlein's group on the attractive Hubbard model, and very nice work from Markus Greiner's group and Wasim Bakar's group on actually using also tunable frustration in the system, where you can introduce kind of T-prime couplings to have very controlled frustration that you add to the system. This is, of course, a very important additional tuning knob that we have. Going now to chemistry, let's think a little bit, let's be bold and think, could, doing something for chemistry also be possible using fermions? And there are actually two ways that have been proposed on this. One would again be an analog way, where you really try to build up the molecule and the Hamiltonian for the molecule in an analog way. The other way would be to think of, can we use, fermionic gates, fermionic quantum computing, to have an advantage over spin-based quantum computing, mostly because in fermionic, if we would use fermionic gates or fermionic quantum computing, we would have the exchange symmetry built in, we have the conservation laws built in, particle number, magnetizations, total spin, all of that is already included in the natural model. So, why don't we harness that? And there have been first proposals how to do that, and I'd just like to flash some recent results that we've been able to look at. First of these orbital gates that we have on these swap gates in the system, and they actually look extremely promising for lithium, where we, I think, get fidelities in the high 99%. We're still evaluating this, so this looks very good. And I think together with the orbital manipulations of the Bloch sphere that I showed you, we have all the toolbox together to really start about thinking about these fermionic quantum computing models and what advantages they can offer, and try them out actually in the laboratory. All right, so in the final part of the talk, I'd like to talk about some quantum dynamics experiments going in a different direction and telling you about recent results on 2D Hilbert space fragmentation and observation of fractons in this system. So a big topic in quantum dynamics, as most of you know, has been how can we actually evade thermalization, the standard process of what's happening. When you take a quantum system out of equilibrium, most of the time it will relax back to some finite temperature state. But we know we have quite a significant systems where we have exceptions of that. Most notably, integrable systems, fine-tuned, of course, constrained to typically 1D settings. Then we have many-body localization, where we can add disorder to the system. Okay, there's the discussion whether it's a thermodynamic phase or not, but for an experiment, finite size experiment, we know that that would also happen. We can have evade thermalization through disorder and interactions. We can have scars, special quantum states, embedded in the Hilbert space for kind of kinetically constrained Hamiltonians, where you have dynamics also which does not lead to thermalization in the system. And also for these kinetically constrained models in a kind of broader sense, you can have fragmentation of your Hilbert space into disconnected blocks, which again can evade thermalization. So how does that typically work? So let's think about our typical ergodic system. There we can, of course, our Hilbert space also splits into many sectors, but this is typically because of global symmetries that we have in the system, and there are typically polynomially many sectors into which our Hilbert space splits up into. Now, if we add constraints in the mobility of the particles to the system, then it's been shown that actually the Hilbert space, in addition to this more kind of trivial kind of factorization, fragmentation, can split up actually into exponentially many disconnected blocks. And in these blocks, if they are small, then you would also evade thermalization because you're not coupling to the outside world. So this would be kind of a thing you can set up. You can set up a system with n particles. That would be your global symmetry. Then you have a conserved energy. And within that Hilbert space of those particles with energy E, you would again find disconnected Hilbert space blocks where you would kind of evade thermalization. So the model where we're going to look at this is the tilted Bose-Hubbard model. So we're going to take a 2D Bose-Hubbard model and we're going to tilt it along the diagonal direction, and we're going to do this in a strong tilt regime, so the tilting is much larger than the kinetic energy, the hopping in the system, but it's resonant with the interactions, so that's important in the system. Okay, strong tilt in the diagonal, but interactions match the energy offset that we tilt between sides. So what are the two things you want to see? Well, in the dynamics, actually, if you have Hilbert space fragmentation, you want to show that you can take two states which have the same energy and particle number in the system, and they show vastly different thermalization dynamics. One, for example, thermalizes rapidly if it belongs to a Krylov sector with a large dimension, and one which has a Krylov sector with a small dimension might show absence of thermalization. The other thing you can do if you have such a kind of Hilbert space fragmented state, you can put excitations, implement defects on top of that kind of fragmented state, and those defects are called fractons, and those fractons have the property that they show kind of a restricted mobility and typically show subdimensional propagation. So in our 2D system, what we expect the fracton to show is basically one-dimensional propagation in the 2D system. All right, so the model that we have, again, is a tilted Bose-Hubbard model. Let me explain that again. So we have the large term here, the large energy term here. We treat the hopping as a perturbation, and that actually separates the Hilbert space into different blocks. And now we're trying to see whether we really can move only in these energy subspaces given by this large energy tilts. So let's look at one of those blocks here. Let's look how that particle can move. We have marking here the equipotential energy lines along the diagonal. And now what can happen, you can have destruction and annihilation of doublons. For example, if a particle jumps from this equipotential line to this equipotential line, that's at an energy delta lower, but if it's compensated by the interaction energy, that's a resonant tunneling process. So this can actually resonantly hop from here to here, and then it can resonantly hop again from here to here. So moving like this around the corner is a resonant first-order hopping process that can occur in the system. Okay? So for second order, you can have processes like that, where the particle hops around the diagonal direction. That process would be kind of resonant in second order. Or you can have doublon hopping processes, which would also be resonant as second order hopping processes happening at a slower energy scale in the system. So our theory collaborators, Frank Pollmann and Melissa Will and Roderick Mössner, they looked at, up to second order, the effective Hamiltonian that you get in the system, and they showed that indeed the system exhibits this Hilbert space fragmentation, as I showed to you before, this fragmentation into these different Krylov subspaces. The nice thing about this model, which every experimentalist will like a lot, is that most of the dynamics occurs in first order. Typically, when you look at those models, the dynamics occurs in higher order processes like t squared over u or something, and then they're very slow processes. So none of the experiments will like that. If you tell them you have a fourth order process that you have to look at over many times, it's not good. But this is a first order process, and we can see the dynamics, this constraint dynamics already in first order. So let's do that. Let's take two states out of the Hilbert space, which have the same particle number and same energy. One is the checkerboard state, if I place my particles according to a checkerboard, or the other state is if I place my particles according to this dimer arrangement. And then let's just look at the evolution of the system given those two initial states. So this is the first state, the checkerboard state here, and you see the checkerboard state is almost locked in completely. It doesn't show any dynamics at all in the system as we evolve over time. If we go to the dimer state, the state 3 here, you see it shows actually very fast relaxation, so completely different dynamics from this first model. And if we take something in between like this Bloch state here. It shows like a dynamics which is somewhere in between the one of a checkerboard and the one of a dimer, again representing these different aspects, picking these different states out of different Krylov sectors, subsectors, showing different thermalization behavior. So if you look at the entanglement entropy of those states, you see that the checkerboard state really indeed has this very, very low entanglement entropy in the system, where if you pick a particle from the dimer sector, you can show that it actually has close to volume law entanglement entropy in the system, corresponding exactly to what I showed you in the dynamics. This thermalizes, this one actually does not thermalize at all in the system. So now let's finally just add interaction. Let's add defects on top of that. We can make a negative defect by displacing one of the particles from the checkerboard to this state, to a lower energy site, or we can make a positive defect by displacing the particle here to a positive energy site. So we make a localized excitation and we look how those spread in the system. So for the negative defect, you can actually see it can resonantly hop. This one can hop along this zigzag line, resonantly along two directions here, but just along 1D. And this is what we see. In the one direction here, this effective diagonal direction, we see a spreading of the particle, whereas if I look in the orthogonal direction, I see basically there's the particle remaining stuck to the original site. Then if I go to the positive defect, it has even more intriguing dynamics. So in the positive defect, if we displace one particle to the upper edge, it can propagate in one dimension, but only to one direction. In the other direction, it's energetically blocked. And that's also something we see. So if we look at the spreading of the particle, it spreads now in one direction, but in the other direction, it's blocked. So finally, we can just test this on a more macroscopic setting, looking at domain wall interfaces between a checkerboard state, the one coming from the small Krylov fragment, and the dimer state, the thermalizing state, and looking at the dynamics of the domain wall if the domain wall is oriented along the equipotential lines or orthogonal to the equipotential lines. So this would be the two situations which we set up. We evolved this system of about 100 sites over kind of 40 evolution times in the system. And you interestingly see that if you align the domain wall along the equipotential lines, you basically see the domain wall remains stable, whereas if you orient it orthogonal to the equipotential lines, you see that the domain wall actually melts pretty rapidly and does not remain stable. And that's, of course, a manifestation of the fractons moving basically mostly along these equipotential lines. So here the impurities can only move along these directions and they will not perturb the domain wall. Whereas if the domain wall is oriented in the orthogonal directions, then these kind of impurities can directly propagate into the other sector and destroy your domain wall in the system. So this is a very nice macroscopic manifestation of this very, very different thermalization dynamics that we have in those systems. All right, just to finish up, where's the field heading next? We've heard a lot about digital quantum simulation in the conference so far. I hope I convinced you that analog quantum simulation is just as exciting and might offer even pushing along the quantum path to quantum advantage even more so right now at least. And I think that's good, something for the discussion session. But maybe, also by now, combining digital with analog is the best thing we can do to combine the fantastic, manipulation and readout capabilities of digital with the very powerful analog kind of evolution abilities we have in the systems. So just to show you just a few in the outlook, a few things that I find very exciting. I find, combining the optical lattices with tweezers, something that's been pioneered by Adam Kaufman in Gila, is a very, very nice direction. And just to show you where we're heading in Munich in this direction, here's a lattice with over 25,000 lattice sites in the system, where you can see each of those individual atoms in the system. Each of those blue spots is a single atom in those systems, and we're manipulating them with tweezers, moving them around with tweezers. And one nice recent result we had on that was to show that we can have a continuously operated atom array where we load atoms from tweezers and we store them in the optical lattice region for a continuous operation of this array. And let me just show you finally this movie where we show that. You have the tweezers loaded randomly stochastically in each run of the experiment. you have the storage zone over here for the atoms in the lattice, and whenever an atom in the lattice gets lost, we just pick up a new atom and replace it on the lattice side there, where it's empty. And this is nice, you know, these are of course first steps towards running these atom experiments in a continuous fashion without the cycle limitations we typically have, and this is, I think, again, promising for computing, simulation, but I think also for metrology, a very exciting direction to have such systems at hand. All right, let me finish up and thank all my collaborators, mostly my theory collaborators first, because it's been a fantastic, you know, endeavor exploring this wonderful world of quantum many-body systems together with them. And if you ask me, where does the value of quantum simulation lie? I think one of the biggest values right now is that indeed we can work together with theory. We can test different theoretical models, METS, DMRG, quantum Monte Carlo, DFT, and really do quantitative comparisons on very clean model systems and learn together about these systems and push forward in making both classical and quantum methods better. On the lithium lab, I would like to just acknowledge the lithium team here, the fermion team. Most of the work I showed you was the work of Thomas Charlepont, who's now back in Paris. The rubidium work, this is our rubidium team. Most of that work, the fracton was done by David Way, and some of the experiments on the double wells were performed on the cesium experiment. That's a collaboration with a team of Monika Eidelsberger, and Alex Impertro was the key person there. All right, with that, I thank you very much for your attention and leave you with this picture from Munich.
All right, are there any questions?
On your, thanks, Manuel. So I was just slightly confused on the Polaron experiments and the whole experiments. Are you looking at are these dynamics, or are you looking at static properties of the system?
It's a good question. So this was static. So this is doping the system, so tuning the chemical potential to values where you're in a very low doping regime, 2% maybe doping or something. So just, you know, you will find, we don't know where the holes are. They're delocalized in the system. We just find one in each shot of the experiment, and then we center the coordinate frame around that hole, and we measure what the spin correlations are. But every time, in every shot of the experiment, it's somewhere random showing up. We can also do what you are asking about, the dynamics experiment. This Marcus has done first experiments on this, where you shoot out, where you take an antiferromagnet, undoped, and now you shoot out one hole, and you look how the polaron is forming actually dynamically. So you can also do a very nice dynamics experiment in this direction. But what I showed was actually static.
All right, one last question right here.
Thanks for the nice talk. I was just wondering, when you mentioned this mapping to these optical qubits, that you map the density to the Pauli operators and so on, is it very obvious that you get the same commutation relations in?
For fermion, well, I mean, the Fermi statistic, if we do it with fermions, the Fermi statistics is built in, right? So we automatically get the right exchange statistics. So if we would have two fermions and put them on a side, we would automatically get the -1 phase factor that you pick up, because we're really doing it with fermions, okay?
Okay. All right, let's thank Immanuel again.